Okay, let's review Unit 2. So you might be watching this for the first time during class, but you can also access this at home and watch it again if it helps you. If it doesn't help you, do your own thing. Just make sure and shoot for that B or better. Alright, so there's 3 standards in this unit, Unit 2A. I can explain how atomic spectra arise and use them to identify atoms. So remember spectra, that's the spectroscope we used where we got lines instead of a whole rainbow. And remember, they actually are unique to certain atoms. So if you see 3 lines that match up with hydrogen, then you know it's hydrogen. I can use my knowledge of fusion to explain nucleosynthesis in stars. Nucleosynthesis, just now I'm kind of realizing we never really defined this term. It just means the creation of atoms. The creation of, well, technically, nucleus, but that's the center of an atom. So you add electrons and you've got an atom. And those that only happens in stars, really. I can describe the life cycle of the sun and connect it to the Big Bang Theory. Alright, so that is exactly what it sounds like. And then on a separate day, actually a week after your Unit 2 exam, you'll take the literacy portion, which Green Dot made, and it's going to cover modeling, arguing with evidence, and then using information and evaluating. So it's going to be a lot of reading for SEP 8. Okay, so part of this first standard is actually doing these calculations. So I want to show you one. We got C equals lambda nu. It says what frequency, so we're looking for lambda at 550 nanometers, so that's the wavelength because it's a length. And so I want to rearrange this. I'm going to divide both sides by lambda, so it gives me nu equals C over lambda. And so now I need to turn lambda into meters. So I have 500 nanometers, but I don't want to plug it in like that. So I use nano is times 10 to the negative 9th, and then I've got meters. So now I can actually plug this in. I know C is 3 times 10 to the 8th meters per second. Do not forget your units. Over 500 times 10 to the negative 9th meters. And so now you can do this on paper, but I give you calculators, so don't be ashamed to use it. Go 3, hit the EXP. Mine's in a different location, obviously, because it's a computer, not your calculator. So this is doing the times 10 to the 8th, divided by 500 times 10 to the negative 9th. Alright, so that gives me, let's see, 3, 6, 3, 6, 9, 12. So 600 times 10 to the 12th. 600 times 10 to the 12th hertz, which is 600 terahertz. And if you do this on calculator, you might get 6 times 10 to the 14th hertz. Those are all the same thing. So all of those are correct. Okay, what else? You also need to explain this idea of the Bohr model and atomic spectra. So if I take a Bohr model for, say, aluminum, aluminum has 13 protons. If it's neutral, that means it also has 13 electrons. Alright, so I put 2. I've got 11 left, so I need another shell. I put 8. Well, I still have 3 left, so I need a third shell. 1, 2, 3. So that would be a Bohr model. And then remember that it's only going to show certain certain lines, because electrons are restricted. So when electrons go between electron shells, they absorb, going away from nucleus, or release, going toward nucleus, light, but only light of the exactly right energy. Okay, so if it's too high energy, then it doesn't do anything. If it's too low energy, doesn't do anything, just goes straight through it. Okay, the other one was about fusion. So what is fusion? Well, let's just define it first. Alright, so fusion, when small nuclei combine to make larger nuclei, consuming a little mass in the process and releasing large amounts of energy. So the basic model for this would be, you have two small nuclei, have them collide at high energy, they make a bigger nuclei, and you get some energy left over. But probably what might confuse you guys is the writing an isotope notation, right? So like, for instance, carbon 12 here, you would write as carbon with a mass of 12, atomic number of 6, and then this is something called a catalyzed nucleosynthesis. This only occurs in high mass stars, which are much higher mass than our sun. So this actually would never occur in our sun. So it says plus a proton, so proton is 11p, or 11h, technically is the same thing. Hydrogen is just a proton. And this gives you a mass of 13, but now it's a higher atomic number because it gained a proton, and you've got a nitrogen. So this is a fusion reaction of hydrogen and carbon. But what this is showing, and I'm not going to go through the whole thing, I'm just going to do a couple so you see an example of how we write these nuclear equations, is that this undergoes positive beta decay, which we saw actually on the Unit 1 exam, and we saw it again, I think, in a challenge problem, is meaning it's going to make a positron. So we take this nitrogen 13, which I didn't really need to rewrite, I could have just taken it from here, and it's going to shoot out a positron, which has basically no mass, but it has a positive 1 charge, which means that this still has 13 mass, but now it has 6 protons, because a proton basically broke down into a neutron and a positron, which I can't really explain why that works. So it would be like that, and then if it gains another proton, 1, here I'll do H this time, we get 14 nitrogen, which is actually pretty stable, but you see it keeps going, and then eventually, here, let's do this last one. No, actually, I'll save that for later, because technically that's actually alpha decay. So it's actually not even fusion. That's one. So this is technically positive beta decay. But these two are fusion. Here, I'll circle them in red. These two are fusion because the nucleus is getting bigger. This is decay, but not technically really fusion or fission because the nucleus is still the same mass. Okay, so fusion gets bigger. Alright, you get the point. Okay, life cycle of the sun. So this is all about fusion. Okay, which the sun is driven by hydrogen coming together and making helium. Although you'd need more than 2 hydrogens. You actually do the proton-proton chain reaction, which was in the challenge problem. You don't really need to memorize that, but if I show that to you, you shouldn't be shocked. Okay, so anyway, you start with, here I'll type them out so you can actually read it. Okay, you start with the stellar nebula, and then gravity pulls that together into a protostar. Once the protostar has enough mass, so high mass, kicks off fusion, and then you have the main sequence star. These burn for quite a while, if it's the mass of our sun, 10 billion years. So we're about 4.6 billion years into it, and we've still got a whole long time to go. Okay, so after the main sequence star, you are low on hydrogen, and so then it gets a little complicated, but it actually contracts, starts burning helium, and then it actually expands into a red giant. Eventually, it'll puff off most of its mass into a planetary nebula, which could potentially combine with other planetary nebulas to form another star, which is kind of cool, actually. Isn't it? I think so. Planetary nebula, and then the core is left behind, but it's still super hot because it was undergoing fusion as a white dwarf. Eventually, and this is theorized, we've never actually observed one of these, but eventually it'll lose all its energy and become a black dwarf, right? Because every time it's shooting off light, it's losing off energy. So if you can see it, it's losing energy. All right, so that's the life cycle of the sun. And then I think the last part of that standard was, how does it connect to the Big Bang Theory? So we know that the universe is mostly hydrogen and helium, right? It's about 75 and 25%. Technically, I think this is closer to 24, and then it's 1% like lithium and carbon, and like basically what we're made of. Carbon, oxygen, that's the 1%. So you're part of the 1%. That's right, like the Occupy, or I'm getting distracted. Okay, anyway. So composition of the universe, how does this connect? Well, imagine in the kind of early universe, and well, at least as we know, there could have been something before, but we don't know. You have these fundamental particles just super close together. It's really hot, really dense, right? And then it starts to expand. So it expands. And as it expands, these particles are now colliding, and it's losing temperature, so less hot. It's still really hot, but less hot. And so these particles are actually able to fuse. But the only ones that are stable is really helium-4. Everything else is unstable. Everything else unstable. Alright, so I don't know that you need to know this for the standard, but from what I understand, helium-4, the next stable thing is actually carbon-12. And so to get this to happen, you need to take 3 helium-4s, basically, so times 3, and get them to hit at the same time. Well, if you can imagine, getting 3 things to all hit at the same time is pretty unlikely. Getting 2 things to hit, okay, maybe. But getting 3 things to hit is going to be much harder to do, and so forming this carbon-12 is unlikely. So everything else is unstable or unlikely. So what does that leave you? Leaves you with helium-4 and a bunch of hydrogen that never actually combined into helium. So it fits, it works. Is it true? Maybe, probably, who knows? But it works. So for now, we'll treat it as true until someone comes and disproves it. All right, so that's your Unit 2 review. Remember also to do the homework, and you can check the homework key. Homework is really good practice. All right, bye-bye.